Hello, this is William from Visual Components. In this video about physics, I'm going to talk about linear and angular damping using Visual Components 4.1. Whenever you are using damping, you are trying to slow down a moving object or dissipate energy like vibrations. For example, you may want to slow down the closing of a door because if the door closes too fast, it might break something, or the door might sway or oscillate back and forth and not close at all. If we think of robotics, whenever a robot is picking and placing parts, you don't want the parts to move or vibrate too much while they're being carried because it may give you an inaccurate solution. In Visual Components 4.1, you have two options for damping. Linear damping allows you to slow down an object moving in any direction, for example, a translational movement along the y-axis. Angular damping allows you to slow down an object that is rotating or spinning, for example, a rotation along the z-axis. To see how this works, I will clear the 3D world, and in my eCatalog panel, go to Models by Type, click Physics, and add an Aero Collider to the 3D world. In the Component Properties panel, go to the Physics Entity tab here, and set the physics type to InPhysics. Run the simulation, so physics is turned on, and now I can use the mouse to pick up the object. And based on how fast and how much force I use to pick up the object, you can see it starts swaying or oscillating around the pickup point. And depending on how much damping we have, the object may come to rest or it just may keep on rotating or spinning. Let's drop it back down to the floor, and this time pick it up ever so slightly. Might still be too fast, so let's see it. It should maybe actually will eventually come to rest. So if you remember physics, there you can have an undamped solution where there's no damping, so the object will just keep on, moving around. You can have underdamped where the object will oscillate back and forth along its equilibrium and then eventually stop. You have overdamped where the object will slow down, take a lot of time before it comes to rest, but it won't go past its equilibrium. And then you have critically damped where the object will come to rest in a short amount of time and not oscillate. So now we can see our object is now at rest. It stopped completely. But I can push it again and it falls down to the floor. Let's reset and take a closer look at how damping is being used in this physical object. I'll go to the Modeling tab. If you don't have access to the Modeling tab, it's okay. You can follow along for now. In the Component Graph panel, select the Behaviors checkbox here. Expand the root node and its behaviors, then select its physics entity behavior. In the properties panel, you can see you have linear damping and angular damping, and their default value is 0. However, this actually uses the default value of these properties in the application. So when linear damping is 0, its default value is 0. When angular damping is 0, its default value is 0.05. So be aware of that. And if we run our solution in the simulation, you can see that with those default values, if I move the cylinder around a lot, it doesn't look like it will stop rotating. But eventually it may just take a lot of time. So let's drop it back down, pick it up, and this looks like it will eventually come to rest, but it will take some time. So let's drop it back down, reset, and to turn off linear or angular damping, you can pass a -1 value. So this disables the force. And now there is no damping in the system, so when we run the simulation, our solution looks like this. So it does not look like this will stop oscillating. Drop it back down, pick it back up, and it's still vibrating a bit. Let's reset. Now for the maximum values for linear and angular damping, you can give the 32-bit float number in programming language. That is the maximum value you can give here. However, we recommend certain maximums for linear and angular damping. Linear damping, we recommend a value of 1000. Angular damping, we recommend a value of 400. So you can use these max values in practice, or you could use a 32-bit float number as the max value. Let's see how it works with the recommended max values. So run the simulation and pick up the part. And yep, you can see there's pretty much no swaying or oscillation. I move the part around, it rotates a bit, reorients, but it's not, swaying or rotating back and forth. So that's just using the max values. Let's reset. And let's see how this works when linear and angular damping are at 1. Run the simulation, pick up the part, and yeah, it's pretty much enough for most cases, and drop it back down. What you can do now is test your own solutions using these properties. What I'm going to do for the rest of the video is do a couple use cases. For example, I'll show you how to make a stack of parts stable during a simulation, as well as how to use a spring with a damping in it to reorient boxes moving along a conveyor. So I will clear the 3D world. Now go back to my Home tab, and I'm still working with my Physics Smart Collection here under Models by Type. I'll add a cylinder collider. With the cylinder selected, I'll go to the Component Properties panel and change its physics type to in physics. I'll then click the component and then use the clone command here on the mini toolbar to quickly copy and paste it. So now I have a pair of 2. I'll add the original component to my selection and clone. So now I have a pair of 4. I'll add the other 2 to my selection and clone them. So now I have a pair of 8 cylinders. Let's stack the cylinders on top of each other. So I'll select the first copy, then use the Move tool to snap its origin to the top face center of the original component. So like so. Let's now do the rest for the other cylinders. You could use your own parts, for example, pallets, a pallet with boxes on it, or a stack of boxes. In this case, we're using these cylinders, which look like toilet paper. That was unintentional, but let's just keep going. So there we have a stack now of 5, 6, 7, and 8. So now all these cylinders are set to be affected by physics and the force of gravity. So when I run the simulation, oi, 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 the stack falls over. So it vibrated or oscillated a bit, and that was too much. Eventually the system broke and the stack fell. Let's reset and see what values we need to use to keep our stack stable. I'll go to the Modeling tab, and using any of the cylinders, go to the Behaviors drop-down menu here, and then add a Python script. So this will allow us to quickly set the physics entity properties of all of these cylinders quickly for testing. So I'm going to delete the lines of code here. We don't need to use the onRun or onSignal event to set the property values. Make the text bigger. To get all the cylinders, let's get the application object first. So app equals get application. I'll then create a list called cylinders, which is equal to, I'll create an inline list here. So C for component, for C in app.components. So this will give me a list of components that are in the application or in the 3D world. And I only want the components that have cylinder in their name. So if cylinder and the component's name. Let's make this a bit bigger. There we go. So this is a quick way to get the cylinders, because if you go to the component graph panel here, you can see that cylinder is in its name. Now you could, of course, not make this an inline list. You could, create for loop and add more lines of code, but this is just a quick and easy way to get all those components. We can check by printing the length of our list. So len for the built-in function, parentheses cylinders, and it should give us 8 for the count, and in the output panel it does, so we have a value of 8. If we select the physics entity behavior here in the component graph panel, we want to set these 2 properties, linear and angular damping. So let's create a for loop. So for cylinder and cylinders, or for C and cylinders, let's find the physics entity behavior. So B equals C dot get behavior. You have to find the behavior by name in the component. So remember, these are all copies of each other. So the name of the behavior in each one is physics entity. Then we want to set the linear damping. So that'll be linear damping. Notice there's no space here in the script, but here in the GUI there is a space. Let's see how it works when linear and angular damping use the default values. So remember, the default value of linear damping when it's set to 0 is 0, and when angular damping is 0, its default value is 0.05. And now to visualize how our damping works in the 3D world, let's use swept volume. So I'll compile the code, and now go back to my Home tab. In my eCatalog panel under Models by Type, I'll expand Robots, scroll down, click Visual Components, add a generic articulated robot to the 3D world, because by default the robot has an output port of 81 that allows you to turn on or off the swept volume. So with the robot selected, go to the Component Properties panel, expand the Actions Configuration section here, go to the output of 81, and then for our swept geometry, when swept volume is turned on, we don't want to sweep the geometry of the robot, so let's delete it from the list. Then click the plus sign here to add our cylinders to the swept geometry list. So we want the first cylinder, the second one, the third one, fourth, fifth, sixth, seventh, eighth. So you should have 8 cylinders in the swept geometry list here. And for those cylinders, let's use a transparent material. Let's use transparent orange, that's fine. The swept geometry will be attached to a new component, and so we can compare results, I'm going to turn on the store geometry option here. So remember, you have to signal swept volume to turn off in order to store the geometry that is swept during the simulation. Otherwise, if you reset before turning off swept volume, the geometry will go away. Let's now tell the robot to turn on swept volume. Go to the Program tab, use the jog command to select the robot. In the Program Editor panel, let's add a set binary output statement. And you want to set the output port 81 to have a true value. And then let's create a delay of about 10 seconds. We want to give our system or our stack of parts enough time to see if it's stable or not. So let's use 10 seconds. And then we'll turn off swept volume. So add another set binary output statement. And set the output port 81 to false. So leave the output value checkbox here unchecked. Run the simulation. And whoa, we get a little solution there. So we can see, using the default values, this is what happened to our stack. So now if we reset, select the swept geometry using the move command, we can move it over here to the side along the y-axis. And let's take a look. So with those default values, the stack kind of fell apart around the second and third part. So let's see if we can change some values to make this more stable. I will move the robot out of the way. We don't need to see it anymore. But let's now use our script. Go back to it. And then for linear and angular damping, let's use -1. So we want to see what the system looks like when there's no damping at all. Compile the code. And to make things easier to compare, I'm going to stay with the robot in the Component Properties panel. Go back to the output port of 81 and change the swept material to be transparent. Let's use transparent blue this time. Run the simulation, and wah-wah-wee-wah. So this is what the stack looks like when there's no damping. And once the simulation stops, let's reset. Select the swept geometry or its component, move it to the side, and we can take a quick look. And it looks like they kind of fell apart around the same time, so there's no visible difference. Let's see how this looks when we use the max values that are recommended for linear and angular damping. So go back to my script, and we'll use 1000 for linear damping and 400 for angular damping. Compile the code, and now let's go back to our robot. Sorry, we do need it. Then for its output port of 81, let's change its swept geometry material to be transparent green. Run the simulation, and oh, it's not going anywhere. So just wait for the simulation to stop. Reset, select the swept geometry component, and move it to the side. Interesting. So this is what the stack of parts looked like using the default values for linear and angular damping. This is what the stack looked like when using no damping. This is what the stack looked like when using the recommended max values. So let's see if we can find a suitable setting for linear and angular damping that doesn't involve using the max values. So to do that, let's go back to our robot, and change the swept volume material to be transparent red. Here we go. So red, there we go. Now go back to our script. And a good rule of thumb is to half the values to work towards a suitable solution. So with 1000, let's half it to 500, and then half to 400 to 200. Compile the code, run the simulation, and we still have the stack staying put. So let's wait for the simulation to stop, reset, select the swept geometry component, and move it to the side. And we can see from these two results that there's a little bit of movement happening here around the fifth part in the stack. So let's see if any more stress or movement occurs in other parts of the stack when we lower the value of our linear and angular damping. So we're just keep on working towards that solution we want. In our script, let's half the value again to 250 and to 100. So 250 for linear damping, 100 for angular damping. Compile the code, run the simulation, and pretty much the same result. The stack is still there. And after 10 seconds, let's reset and move the solution to the side. And still a similar result, so let's start getting a bit bigger. So half of 250, 125, half of 150. Compile your code, run the simulation. And it looks like we're still getting the same result almost. So after 10 seconds, let's reset, move it to the side, and yep, still about the same way. So let's now jump ahead a bit. So instead of half of 125, let's say that's like 60. Let's go to 30 for linear damping. And half of 50 is 25, so let's go to 12. Compile the code, run the simulation, and that time we got some movement in our stack. So after 10 seconds, let's reset, and then move it to the side. And this is actually interesting. It's good that we're using swept volume because we can see where a lot of the movement is coming from in the stack. So at the bottom there was some more stress here, so it was moving around a bit. And that's why you see more red color here, because swept volume is an iterative process. So if it's moving in a different location, it will render more color or a deeper pigment. And you can see here, so this side of the stack is kind of clear, not a lot of movement, but there was movement leaning in this direction here, and all the way along this side as well. And if we go back to our first test, we can see that that's kind of where our system is falling apart here on this side, in that direction. Interesting. But it's still staying upright, so let's see what actually will cause this deck to start falling over. In our script, let's half 30 to 15 and 12 to 6. Compile the code, run the simulation, and it's still staying put, but there is some movement. And after 10 seconds, reset, move the swept geometry to the side, look at the results. And yep, it seems like we're getting closer and closer to a system failure or the stack falling over. Let's now try half of 15. Let's use 7 and 3 for angular damping. Compile the code, run the simulation, and it finally topples over. Okay, so we know once we get to 7 for linear damping and 3 for angular damping, that the stack will fall over. Interesting. So reset, and let's now move it over here to the side. Great. Now, one thing I do want to cover really quickly is how you could avoid using damping altogether and try using a solver position and velocity iterations. So if you don't want to mess around with the linear and angular damping, you can increase the amount of iterations it takes to solve the position and velocity of your physical bodies or objects in the 3D world. For example, let's set linear damping to -1 and angular damping to -1. And then let's now set the solver position iterations and solver velocity iterations properties of our physics entity behavior. So let me select a cylinder and go back to the modeling tab and select a physics entity behavior to show you. So you can see here, these are the two properties I'm talking about. So if you're getting frustrated or you don't know what values you have to use for the dampening, you can try using these properties first. So instead of using linear and angular, let's use solver position iterations. And when this is 0, its default value is 4, if I remember correctly. And for the solver velocity iterations, when it's 0, its default value is 1. So we already know what the system or the stack of parts will look like when linear and angular damping are turned off. Basically, it looks like the blue one here. So let's see what happens when we use, say, 40 for solver position iterations and 10 for velocity iterations. Compile the code, and let's use a different color this time for the swept geometry. So I'll go back to the Program tab and select my robot. And then in the output port of 81, for the swept volume, let's use a different transparent material. Let's use yellow. So transparent yellow. And this time, we're not using any damping. We're just using the solver position iterations and solver velocity iterations. So we're increasing the number of times it will calculate or try to solve the position and velocity of our objects. Run the simulation. Wow, there you go. So this time, without using any damping, we were able to use those solvers to get this stack to be stable. So after 10 seconds, reset. Let's now move our swept geometry to the side and look at the results here. So now we can see we still get a lot of movement here along the side of the stack and a little bit down at the bottom here, but overall it still gives us a kind of similar result that we had here, where there's not a lot of movement on this side of the stack. So we know this is stable using 40 and 10. Let's half the values now and see what happens. So 20 for solver position and 5 for velocity. Compile the code, run the simulation, and whoa, that does not look stable. We have a leaning tower now. And after 10 seconds, let's reset. Move it to the side. And yep, so now we have a lot more movement leaning in this direction. One thing to notice when using these solvers is that if you move the parts at all, like an external force, then of course it would help to have dampening to kind of slow down the objects or resist that movement, because the solvers will just solve a position, not necessarily be a restriction or a force against the movement. So if we set now 20 and 5, run the simulation again, and I push the parts a bit, you can see that they don't really have enough dampening or friction to stop them from moving. But now let's try that again with some damping value. So let's move our solution to the side. There we go. Reset. And now for linear damping, let's use 20. And for angular damping, let's use 5. Compile the code, run the simulation, and it is quite stable. Let's move apart. And yep, that's pretty much not going anywhere. So we can run the simulation and try to keep on moving it. And it did fall over, but it's still kind of stable just by using a little bit of dampening here with the solvers. Okay, let's reset. What you could do is you could save this for your own record and go back and kind of review all the swept geometry we created for our test cases. What I'm going to do now is show you how to use damping with a spring. In this case, a swing arm of a conveyor. To get started, clear the 3D world of all components. I'll now go back to my eCatalog panel, and in the Physics Smart Collection under Models by Type, I'll add a physics conveyor and a physics feeder. You want the feeder to be plugged into the conveyor, so when you run the simulation, the feeder creates these parts, they move along the path, and they fall down to the floor here. Let's reset, And with the feeder selected, go to the Component Properties panel, change the product from cylinder to box. Now go to the Product Param tabs and change the box height, length, and width to 100. Run the simulation. And now we get these teeny tiny boxes. Let's change how often the boxes are created, because now they're being created a bit too fast. Let's reset, go back to the default tab in the Component Properties panel, and change the creation interval from 1 second to 8 seconds. Run the simulation. Now we have one box, and 8 seconds later there should be another box. And yep, here we go. What we want to do now is add a swing arm to the conveyor that can collide with the boxes and change their orientation or position along the conveyor. Let's reset. Select the conveyor, go to the Modeling tab. I will now create a new link in the component, and using the Move tool, I will offset the link to be at the midpoint of the edge here along the conveyor side rail. In the Link Properties panel, make sure the rotations along the X, Y, and Z are at 0. Now add a block or box feature to the link. For the block properties, I'll change its length to be 250. And its width to be 10. I'll now rotate the box along the Z-axis by 90 degrees. I'll now expand the physics section here and give the box a box collider. Notice the feedback in the output panel. This also added a physics entity behavior to the link I created in the conveyor. So if we go to the component graph panel in the component node tree, expand link 1 and its behaviors, and there's the physics entity behavior. Let's now see how this works when we run the simulation. So here come the boxes. They collide with our block here, and eventually they are turning, but it doesn't look too good. So now let's make our block have a swing motion. So I'll reset. I'll now select the root node of the conveyor in the component graph panel. I'll go to the behaviors group and add a physics joint. In the properties panel, let's attach the joint to link 1 in the conveyor. For the twist motion, this is mostly concerned with the rotation around the XY plane, so let's lock this. For swing motion 1, this is, I believe, the X or Y axis. We can leave that at free for now, but let's lock the second swing motion. And now for the offset of our joint, let's drag it to be where the midpoint of the edge here is in our block. Let's also adjust the orientation to be 0 along the X, Y, and Z. But now let's rotate the joint's offset along the Y-axis 90 degrees. So now the Z-axis of the joint is pointing this way along the X-axis of the conveyor's path. So what we expect to happen is our block here, it should swivel or swing in this direction. Let's now run our simulation. And nope, that doesn't happen. Let's find out why. So let's reset. The swing 1 motion is set to free. Let's go to our physics entity behavior. And then the properties panel, we can see that, the physics type for the physics entity behavior for the link we created is kinematic, so that's why it's not moving. It's not being affected by the force of gravity, and we don't want that. We want our block to kind of move freely. So since the block is anchored to the root node of the component, it won't fall down and hit the conveyor's path. So it's safe to set it to be in physics. Run the simulation. And yep, wow. So now the box collided with our swing arm here, and now it's just going to keep on swinging because we're not really using any damping or force to slow it down. And yep, let's now reset. So that was using the default values for the linear and angular damping. Let's try using -1 to see how the system works with no damping at all. Run the simulation. And pretty much similar result. Reset. Let's now try the max values, so 1000 for linear and 400 for angular damping. And you can see the block does move, but its joint doesn't have any setup right now to say, okay, once you go to here, swing back and stop at the rest position here, or the equilibrium. So let's see if we can get that to work. I'll reset, and then I'll go to the physics joint I added to the conveyor. So select the behavior. And then in the properties panel, instead of using a free setting for the swing 1 motion along our x-axis, let's set it to limited. Expand the swing limit section here. And let's see what happens when we use 45 for the y angle limit. Run the simulation. And we get a little bit of stiffness, but it stays there, so we probably don't want that. Let's reset, set the y angle back to 0, and this time we'll use a soft limit for the swing motion. So by default, the spring force is set to 1, and damping is at 0. Let's see what that looks like. It's a bit too stiff, so we want it to kind of swing out a bit and then swing back. So let's reset and see what happens when damping is at 5. Run the simulation, and yep, it does swing out, and now it's swinging back, but this looks like an over-damped solution because it's taking too much time. It's really slow, and it won't go past its equilibrium. So what we're looking for is a critically damped solution where this block here, the swing arm, will go back to its rest position rather quickly. So let's reset, and then instead of using a spring of 1, let's use 0.5 and see if that does anything. Nope, still too slow. Let's set the dampening back to 0. That's still too stiff. We could try a different route. Let's go to our physics entity in our link 1 node and set the linear and angular dampening back to 0. And then let's see what happens. Because now we have our physics joint using the swing soft limit. And we do get a bit of spring here, but this actually looks like an underdamped solution, yeah. So you can see it is swinging out, and then it swings back, but it is oscillating about its rest or equilibrium a bit until it settles. So we don't want that. Let's go back to the physics joint. And then for the spring limit, let's use some damping here. Say 2. Run the simulation. And that looks okay. I think we're getting there. Yeah, that looks fine. Let's see what happens when we use 1 here for the swing limit damping setting. Hey, that looks fine to me. Okay. So yep, there's one simple example. Let's see if we can have a movement along a linear movement actually along the z-axis here of our joint. So if we reset, remember our joint, its z-axis is going in this direction. So for our swing 1 motion, let's set it to be locked. And then for our moving along the z-axis, let's set it to be limited. Run the simulation and see what that looks like. It's very stiff, but you can see it tried to go this direction, then go back here. Let's reset and expand the linear limit section here in the properties panel. Let's use a distance of 200 and see if that can give us something. Nope. Set this back to 0. Actually, no, let's keep the linear limit distance at 200, but let's change the restitution from 0 to be, say, 2. So this probably should give us some spring in the movement. Oh, and that was all over the place. So let's reset and set the linear limit back to the distance to 0 and use extend to, say, 200. So we want some freedom here. And yep, we did get some spring there, but I think the restitution is too much. So let's use 1. And that looks okay. So what we're trying to find is a moment where the linear damping is really working, not the angular damping. So here you can see when the boxes collide, our swing arm, it swings back in a linear motion. Then the restitution and the extension we're using, and that's that looks underdamped or undamped because it just keeps on swinging back and forth, but it actually is settling after some time. So let's reset and see what happens when we use a restitution of 1.5. I think we actually need to go lower. yeah, there's too much springiness. So let's use 0.5 for the linear limit restitution. And that looks actually over-damped. Yep. But you can keep on experimenting with these settings. But okay, this completes the video. If you have any more questions, please feel free to visit our forum at forum.visualcomponents.com. And as always, I hope you have a wonderful day.